So if you recall from part 9 on lipids, we talked about sphingolipids and their structure. So sphingolipids have a sphingosine backbone, which is highlighted here in purple, and they have an acyl group attached at carbon number 2 of the backbone via an amide linkage here. And then the polar head group is basically this X here, and this X it could be a phosphoalcohol, or it could be a sugar of some sort, or sugars. So how are these things made? Well, there's 4 steps, so in that sense they're similar to the way in which glycerophospholipids are made, because there's also 4 steps to make those. What's the first thing that we have to do is we have to form a sphingonine backbone. Sphingonine backbone. And how many carbons is that? Well, as you can see from here, there are 18. And 16 of those carbons come from palmitoyl-CoA, which is an activated fatty acyl-CoA, and 2 of them come from an amino acid serine, which actually has 3 carbons, so we'll have to pay attention to where that 3rd carbon actually goes. The second thing that needs to happen is that we need to attach a fatty acyl-CoA as an acyl group to the backbone via an amide linkage. That's where we see that there. And at which carbon of the backbone does this occur? We can see that occurs at carbon number 2, so C2. And I'll even put that in orange to indicate that we're talking about that carbon numbered in orange. The next thing that we need to do is have the desaturation of the sphingonine backbone between carbons 4, so let's again orange. Let's do C4 and C5. So we can see that right here between carbon 4 and carbon 5 in purple here, there is a double bond. So that has to be input in the 3rd step. And the question there is, what's the name of the parent compound formed by this step? In that step, what will happen is that we will make the parent compound of sphingolipids, which is called ceramide. After that, the last thing to do is have the attachment of the polar head group, depending on what it is. So these first 3 steps here occur in the smooth ER, and this last one occurs in the Golgi. Okay, cool. Let's move on and see these steps. So first up, we've got serine here, the amino acid, and we have palmitoyl-CoA, the activated fatty acyl-CoA. And so these 2 are going to come together to form the sphingonine backbone, and only 2 of the 3 carbons in serine are actually going to be part of the backbone. It's this first carbon labeled carbon number 1 here, and carbon number 2 right above it, the alpha carbon. And actually what leaves is this 3rd carbon here, that's part of the carboxyl group. That's going to leave as carbon dioxide when these 2 condense. Another thing is that the coenzyme A will also leave, and essentially what will happen is that we'll have the chain of palmitoyl-CoA connected to the serine. Basically, carbon number 2 is sort of going to be connected to carbon number 3. And that's what we get over here in this molecule, 3-ketosphingolipid. So we've got these 2 carbons here from serine, and the rest of this molecule coming from palmitoyl-CoA. Alright, so serine and palmitoyl-CoA make up the backbone in that first step. The next thing that we need to do is that we need to take this carbon number 3 here and turn this ketone into an alcohol to give the molecule sphingonine, to form the actual backbone, because that carbonyl does not exist in sphingolipids. So that needs to be reduced, and the reducing agent for that is going to be NADPH. So now we have the alcohol, and we've made sphingonine. So step 1, forming the sphingonine backbone, is complete. The next thing we need to do is add the acyl group via the amide linkage. So that's what happened here at carbon number 2 of the backbone. We connected an acyl group to that nitrogen there. So we go from an amino group to an amide, and we need to have an acyl-CoA come in, and the coenzyme A will fall off, and that will give us N-acyl sphingonine, which is just sphingonine with an acyl group attached at the end of the backbone. So that's step 2 there. Step 3 is going to be inputting the desaturation between carbons 4 and 5. So right here there's a single bond that we're starting off with. We need that to be a double bond. And the enzyme that's going to accomplish that is called a mixed function oxidase, which we've mentioned a couple times before. And that, of course, requires NADH as well as molecular oxygen. And that'll give us ceramide, which is the parent compound of sphingolipids. So I'll just make that note here. The parent compound of sphingolipids. Okay. Now, once we have ceramide, the last step is simply to attach the polar head group. So that'll be step 4. So we can either have a situation in which the polar head group is some sort of sugar or collection of sugars. In this case, I've drawn glucose here as part of the polar head group, and that'll give us a cerebroside. Or we can have a phosphoalcohol portion as the polar head group to give us a sphingomyelin. So let's start with the cerebroside up here. In order to get a cerebroside and attach this sugar on here, this is specifically glucose, that needs to come from an activated glucose, so specifically UDP glucose. And we've seen UDP glucose in glycogen synthesis. So UDP glucose is basically an activated glucose, right? This is activated, and that's going to come in, and the glucose will be attached while the UDP will fall off. We could also add galactose using UDP galactose. Okay. Once we create the cerebroside, we can add more sugars to give us globosides, and if we add a sialic acid or even more sugars, we can get gangliosides as well. If you're unfamiliar with these terms or they seem kind of fishy, I would encourage you to go back and watch the sphingolipids portion of the lipids series. Maybe I'll have a link to that somewhere. Now, if we wanted to make a sphingomyelin, we'd have to add a phosphoalcohol portion. Where is that phosphoalcohol portion going to actually come from? Here, the way I've drawn it, I've drawn phosphocholine. So this is choline over here. That's part of this sphingomyelin. And so where does that actually come from? That's going to come from an actual phospholipid. So in this case, we're talking about adding choline. So we'd have to use the phospholipid phosphatidylcholine. Phosphatidylcholine. The entire phospholipid would come in and basically give its phosphocholine portion to ceramide to give the sphingomyelin here, and what would be left of the phosphatidylcholine would just be the diacylglycerol portion. So basically the phosphoalcohol portion of phosphatidylcholine would come off and attach to ceramide to make the sphingomyelin here. This could of course work with other phospholipids, or glycerophospholipids specifically, like phosphatidyl ethanolamine or phosphatidylserine. So this here is a little bit different than glycerophospholipid synthesis, where we just added a CDP choline or a CDP ethanolamine to get the basically the polar head group attached to give our final product. In this case, we actually have to take another lipid and basically steal its polar head group. So I hope that video wraps up sphingolipid synthesis fairly well. Thank you for watching.